Good morning, everyone. So my name is Sriram, and so this workshop will be about dynamic voltage stability. And I think I already gave a presentation on Monday where I just briefly explained what we are doing in the project and how we are approaching the voltage stability problem. And I also explained that inverters can be seen as impedances, and changing the inverter's impedance would be a path towards achieving global stability of the power system. So today's presentation will contain these topics. So first I would start with again the Middlebrook Criterion, because that's the starting point for DC systems. So I would just explain in short. But this time I have added some examples of how systems can be designed based on this criterion. Then we would look into the generalized Nyquist criterion, which we are using for characterizing inverters and characterizing the stability of the inverters. I would reiterate a little bit on PLL dynamics and how PLLs can be designed and what impact PLL causes towards what PLL means for instability or how it affects the stability of the inverter. And we'll also see how the PLL reshapes the inverter's output impedance. Then I would give an example of harmonic instability. We'll look at a simulation example of a single phase inverter. I think this is the example that we'll also do in the exercise today with Opal RT. And I would explain how the grid impedance is going to affect the stability margins, and therefore you can see how the current waveforms and the voltage waveforms are impacted by the grid impedance. And so in the exercise later in the evening, you can also play with the parameters to really see how the control bandwidth, when the control bandwidth and the grid impedance would start interacting. And the last would be just the new role of inverters that we are proposing from the project RESERVE, and what field trial is planned. And we also have a device that is coming out of this project, so I'll also explain about this device in detail. So, so this would be the first topic on Middlebrook criterion. So basically, as I explained already, if you have two systems and you want to interconnect these two systems, then you want to, before you do that, you want to theoretically evaluate the stability so that the interconnection is stable. So the idea is to break the subsystem at the point of interconnection and then model the impedance as seen from the point of interconnection on either side. So you can have a source and a load impedance, and which would result into a model like this. And from this equation, you can know that the Middlebrook stability criterion is defined in this way, where the source by load impedance, the magnitude should be far less than 1. This is the idea. So Middlebrook only looks at magnitude, and as I already explained, it's a highly conservative idea, which means the system can not satisfy this criteria and still be stable. But if you do a design which satisfies this criteria, then you can then you have a system which is extremely stable because it's the highest form of stability, and you have very less interactions happening. So so that's the idea. But the system's response will be slow. So it's a compromise between performance and stability. If you want good stability, then you have low bandwidths. If you have higher bandwidths, then you are going towards instability. So what I explained is just captured by this figure. So here you have a stable system, which doesn't, this is the critical point of -1. The plot shouldn't encircle this point. So this plot is actually stable, but according to Middlebrook might define this as his circle of that is this impedance ratio, should be less than some, let's say 0.7. So this could be a circle of that magnitude from here. And according to Middlebrook, this would be unstable system, but it's a perfectly stable design. So therefore you have other criteria which relax this criterion, and one of them is, so some of them could be mentioning gain margins or phase margins and defining a forbidden region. So that means according to the forbidden region criteria, this plot cannot enter the forbidden region. It can stay anywhere in this real imaginary plane. So, and then you have another criteria which I also explained called the passivity-based stability criterion. We also will see an example based on that. According to the passivity criterion, this plot cannot enter this negative side, the negative real side. So the plot should only stay on the right side of this imaginary axis. And that is also a very conservative idea, because a plot can still enter and be stable. But passivity is really nice, because passivity means that if the plot exists on this side, then this means that the system is not going to interact. There is not going to be any interaction. So if suppose the converter is connected to a grid, and if you make sure by the control design that the converter is passive, then this means that the converter will not react to the grid disturbances. That's why passivity is really nice. And we also recently published a paper on how to design the control loops of a DC-DC converter such that it's passive, which means it's not going to interact with the grid at all or react to the grid disturbances. So the first example is this. This is how it all started. This whole idea of stability, voltage stability based on impedance. It's from a guy called professor called R.D. Middlebrook. So he wanted to design. He has a DC-DC converter, and he wants to design an input filter, because, for example, DC-DC converters like the buck converter, in this case the input current would be pulse, and this means you are drawing high harmonics from the source. And grid codes might not allow you to do that. So therefore you need to add a filter in order to have a smooth input current that you draw from the source. And this input filter might interfere with this converter design, and it could cause instability. So the idea is, for example, we consider a LC filter at the input side. Okay, so you can model the impedance of the filter like this. So you have the Thevenin equivalent as seen from here is this impedance, and parallel you have this impedance. So that's the Thevenin equivalent impedance of the filter. And then you try to design these filter elements such that you are stable. And the input impedance of the converter can be obtained either experimentally, or you can also do theoretical modeling. So I don't want to go into the details because it's too theoretical, but you have methods called state space averaging. If you're into power electronics, you would probably have learned it. So you can apply those methods to model this impedance, because as you know that in a power converter which is having switched states, you need to so it's driving a different circuit at different switching period, right? When the switch is on, you have a different circuit. So you need to have a sort of averaging to explain the behavior of this converter. So that's why you have such methods called state space averaging, and there are more advanced methods called generalized state space averaging. But just to give you an idea that you have methods and you can model converters. And if you want to do it experimentally, the idea is to connect a source to the converter and start injecting some kind of sinusoidal signals and try to measure the amplitude and phase of the current that's drawn by the converter. Then you can get the input impedance of the converter, both magnitude and phase. This is the idea. You can either obtain it via data points. In this case, it's modeled as an transfer function, which is by state space averaging. And once you get that, you can evaluate the ratio, and you can check if this filter is okay. If it's not, you can try to add some damping elements to damp the resonances that could arise because of this LC filter. So this would be a later step. And again, you can repeat the design process. Again, modeling this impedance, modeling, this is already modeled. That doesn't change. You can verify if this damping is good enough. So that's the design example. So going into equations would be tedious algebra. So I just don't go into that. And you can already find it. It's started from the 1970s. So then we can go a step further. So now we want to connect two converters. So this is converter A. For example, this could be a dual active bridge, three-phase dual active bridge. I think Professor Didankar explained that, and we also saw one. If you came for the lab tour to the other building, you saw the converter. So it could be this converter, which drives another converter, which tries to drive another load at another voltage level. So you could have this cascading. And again, you have to make sure that the cascading is going to be okay. So the procedure would be first to model the output impedance of the converter, then from this interconnection point, because after the converter you could have some filter which is with the converter actually, or added later in order to have a connection to the bus or to the grid. So similarly, a load side converter you might add some input filter later in order to control the harmonics current drawn from the grid. For example, in this case, let's say this node is the grid. So in that case, you first have to model the local impedance of the converter. Then you try to split it up and try to model the entire impedance as seen from here. And you can repeat. So this is the idea for checking the stability of the interconnection. And so the control parameters of this converter and the control parameters of this converter decide the stability of this node. So you can try to come up with a design-based approach in order to maintain the stability criterion. So this whole idea is design-oriented. So now let's look into the passivity-based stability criterion, where I said it's a very nice way of enhancing stability, because the converter wouldn't react to disturbances. So let's say that you have a power system like this, a DC microgrid. This is a model of a shipboard power system of a naval application. So these are source side converters which feed power into the bus, and these are load side converters. So for example, these are all buck converters, these are all dual active bridge converters on the other side. And these converters are non-linear in nature, as seen from the bus, because they are acting like a constant power load, which I explained on Monday. And this is a linear load, which is just a resistive load directly connected to the bus. So you could have all sorts of combination like this. So an equivalent picture to look at this thing would be this. So you have this is the bus, the plus and minus, yeah, the plus 6000 volt or whatever voltage you have, and 0 volts, this is the rails, and you have all the converters connected, source side converters connected to the bus. You have this is just, I'm just showing one here, but you have n number of them, all the load side converters connected to the bus, and you can have the impedance model done for each of the converter. And if you make sure that this design, this local design here and make sure that this impedance is passive by your control, because you can modify the converter's behavior by the control. So you can make sure that all of these impedances are passive. So at the end, since all of them are connected to the same nodes, they are all in parallel. So the parallel combination of all the source impedances and the load impedances can result into one single impedance called as, let's say, Z bus. And now the stability criterion for the entire power system is just to make sure that if this Z bus is passive. So for example, this is a plot of simulation that is done of the modeling that is done for all the source side and load side converters. And you can see that the Nyquist plot, it results completely on the right half plane. It doesn't enter the negative side. This is a passive design. So in this case, none of the converters are going to engage or react to disturbances. It's going to reject disturbances. That's a passive system. So any questions until this point? Okay, so that was about the first topic. Now we go into AC systems. So it's the same approach that I followed on the other day. So just a little bit of theory again. So you have the three-phase quantities, and three-phase quantities, so they are sinusoidal, and you want to apply the impedance techniques, so it should be converted into DC system. And the way to do that is to define a rotating coordinate system which rotates at 50 Hertz with the sinusoidal, the phasors of individual phasor signals. And therefore, the reflection of the rotating wave or rotating vector of current or voltage on the rotating reference frame would be static or DC. That's the idea. And this is the transformation which helps to do that. So the main advantage of doing this idea is to, first of all, have it as a DC system, and therefore you can just design simple PI controllers and not proportional resonant or higher order controllers, which could be a little bit difficult. So this is going to be easy, but the challenge comes in designing a proper PLL. So which I'll explain a little bit later of why PLLs are quite challenging. So just to give an overview, because many might not be into control system design or for inverters. So looks something like this. So you have the converter here. This is the inductor. This is the capacitor. You're taking the measurement of the bus voltage and the inductor currents, and then the grid voltage is passed into this block called the phase lock loop or the PLL, which gives the synchronization angle, and this angle is used in all the conversions to convert from the ABC to DQ or DQ to ABC. And the controllers are designed completely in the DQ reference frame. So this is just the basic picture. And then a little bit complicated step from that is the modeling of inverters. So I was explaining in the DC scenario that the input impedance of converters or whatever can be modeled mathematically. So this is how we model the impedance of the inverter in DQ domain mathematically. So I can quickly explain how this works. So this here is the control transfer function. Takes in the control input, and the output is the current, the grid current that is injected into the grid. Then you have the grid voltage, which drives a part of a current, because there is some impedance of the inverter inherently, because after the so this is here you have the switches, and this is the filters. So if suppose you have the breakers closed and the inverter opened, then there is some current that's driven by this LC. That's the open loop impedance. So it's the natural current that would be there if the filters are exposed. And then, so this is the inverter itself. These two are the inverter. That's why I denote it as inverter power stage modeling. Output is a current, that's something that's measurable. This is what I can measure. The linear combination of these two is what I can see physically, or that I can measure, which is fed back. This is my reference. This is how much current I want to inject into the grid. They both are subtracted because we want the error to be 0. This is the error. I want the current error to be 0 because I want to tell the inverter you have to inject I reference amount of current. Then you have the the controller. This is the simple PI controller that I was talking about, a first order controller which does the tracking. And what I skipped is when you model from ABC to DQ, you have some coupling between the D and the Q. And to get rid of this coupling, we have this decoupling block, because we know exactly how it is coupled, which I'll show in a minute. I think I have it here. Yeah, for example, just to so this is the D-axis current equation. This is the Q-axis current equation. In the D-axis current equation, you see all terms. Actually, I wrote it in phasor notation. So you can, if you split it up into real and imaginary part equation, okay. This is the complex equation. So I should have written. Then you would have 6 equations. Okay, each one is real and imaginary. 2 equations, 2 to each. So if you write it, split it into real and imaginary part and write this down, then you would see that the D equation would have a Q term and the Q equation would have a D term. And this omega times I is the exact term that needs to be eliminated. And that is what we do here. With the opposite sign, we try to cancel it out here. That's the idea. So that D and Q are completely decoupled. Any change in D would have very minor effects in Q, because our assumption is linear systems, but in reality it's non-linear. So you are only trying to kill the linear terms, but there could be non-linear terms which somehow show as an impact. So you are not completely eliminating, but to a good extent. Then now our goal is to get the output impedance of the inverter that you would like to see from here, right? Because this is the point where I connect to the grid, and I could have grid impedances after that, but I want to see the impedance from here. So that can be formulated, that is this equation, which is nothing but the mapping from the output current to the grid voltage. So that is the rule. So I have to remind you that these are multiple input, multiple output systems with 2 inputs and 2 outputs. So you might have learned in control systems that simple block reduction techniques, which cannot be done here, because what you would have learned, what they teach in courses is just for single input, single output systems, which is easy. This is a multiple input, multiple output system, and each of them is a matrix. So there is a procedure, there is a nice rule which I always use called the generalized multiple input, multiple output system rule. So the idea is to start from here and go there, and if you encounter a feedback path, then you include the feedback transfer function. That's the idea. So you start from here, and you immediately, and you want to go there, but you immediately enter a path where you have a feedback path through this way. So then you start with I plus and put all the transfer functions that you encounter in this direction and times this over here. So that's the idea. It's if you get used to it, it will be simple, but yeah, it's a little bit complex, but it can be done. So once you have this, so this is the DQ domain transfer function model of the inverter. So what I'm trying to say here is you have your inverter, which as I already explained is like a current source. You want to inject some amount of current. So the equivalent modeling will be a current source, and in shunt you have this impedance that you just derived for the inverter. So this would be the closed loop impedance model as seen from the point of common coupling where the inverter is connected. Any questions on this? It's just an abstract theoretical idea of how it is done, and you will later see that how it all comes together. So just to explain again, really short with this diagram. So you have the inverter with the switches here, with the filter, and just in case if you are wondering how these transfer functions can be obtained, then they are obtained from the state space equations, and the state space equations are nothing but writing down the differential equations for the energy storing elements such as inductors and capacitors. Then this is basically the state space formulation. From this you can get those transfer functions. So that's how you get all of them. So for example, the control transfer function is the mapping from this variable to the current variables, and the open loop impedance, the driving impedance, is obtained from the mapping from this variable to the current variables again. So you can rearrange your A and B matrices in the way you like to have whatever mapping you want. Then you can get those transfer functions. Once you get them, then you plug it into this formula and you get the inverter closed loop impedance. So to summarize, the closed loop impedance is a function of the inverter's open loop transfer functions and the controllers. The controller shows up in the inverter closed loop impedance. So the controller affects the way inverters behave. So this is the conclusion from here. So once you get the impedance of the inverter and the impedance of the grid, then you can calculate the stability by the impedance ratio again, the source by load. It's just written in matrix notation by Z times Y. And now I'll just quickly explain how to get the plot. Because in the single input case, you just had one transfer function for which you can just do Nyquist of that plot and you just get the plot in MATLAB, for example. But how to get this when this is the transfer function matrix? If you just use the Nyquist command, you're going to get 4 plots. That's not correct. MATLAB thinks that there are 4 single input, single output systems and it gives you 4 plots. But this is a multiple input, multiple output system. So just going to shortly explain the procedure of how to do that. So let's say that you got this impedance ratio, right? It's a function of frequency, right? Then what you do is you create a frequency vector. Let's say you're interested from 1 Hertz to 100 kilohertz. Okay, then you plug in this value of frequency into this L of j omega. So now it's just 4 numbers. It's 2 cross 2 matrix. Then you can calculate the eigenvalues, and you can do this for all the frequencies that you chose. So therefore, what you end up with is 2 eigenvalues which are functions of the frequency, and just plot those 2 eigenvalues. That's it. That's the plot. Then the way you do stability analysis is you apply the Nyquist theorem considering both the plots. So if you, I don't want to go into the Nyquist theorem again, as it goes into a lot of control theory, but you would basically see the number of encirclements the plot has, and you check with the right half plane zeros. And that procedure needs to be done considering the 2 curves. So it's as simple as that. So this is the idea of how to get the plot. So, and just to give you some modeling examples of inverters again, why I'm stressing on all of this is because if your goal is to reshape the inverter's impedance, you're going to do some control action. You're going to either take the grid voltage, put it into some controller and feed it somewhere else, or in this case I've measured the grid current. There is some external controller which changes the capacitor voltage set points. You're going to do some action, and until and unless you model, you don't know how to design this controller. So that's why modeling is super important. So again, it's just the same rule of applying the generalized multiple input, multiple output rule, and once you get the hang of it, you can just write down this equation in one stretch. And in this case, for example, this is again the same current controlled inverter which needs to inject a certain amount of current. For example, a PV inverter. right? And if I want to dynamically control how this PV inverter should behave, then this is the architecture that I choose in order to establish how to control the dynamic performance of the inverter. Then I can model the closed loop impedance in this way. So you can see here that how this term that I newly introduced, because this is my term, this is how conventionally inverters are done, and then suddenly I introduced this term, and now you can see how it affects the performance of the, or how it reshapes the impedance. So this term is nothing but this is the external current controller. So it modifies the external current control term. That's how the inverter is behaving now. So if I want to slow down the rate at which the inverter should inject current, or speed up or increase the bandwidth, in other words, then I can just play with this and make sure that this has a certain bandwidth, this entire term, because this is representing how the capacitor voltage, the reference is going to the inner controllers. So this is the idea, and same idea can just be applied. So that was for current control, and now this is for voltage control. So in the case if you want to have a grid forming converter where voltage is enforced on the grid, for example in microgrid applications, the exact dual of what I showed before, exact dual can be applied, and you can try to control how the voltage control inverters need to behave in the grid. So the design of this could be any linear loop shaping techniques can be applied. For example, I applied the H infinity norm based technique. So this means that you try to minimize for example, the goal was to minimize the harmonics or the resonant peaks and try to design this controller. So it's very open on how to design this controller. There is no one correct way or right way. So therefore I just won't go into that, and it will get too much of technical detail already. So I'll just stop with this in this topic. And now we just look at how PLLs are going to affect the inverters. So the PLL is basically trying to track the grid, trying to get the phase of the grid so that the inverter is in sync with the grid. So it gets the grid voltage measurements. It has this DQ transformation, and for example in this case we want to align the D axis with the grid, then the Q voltage is tracked to 0, and this is the controller that we need to design to make the PLL have satisfactory performance. And this part here with the integrator is called as a virtual controlled oscillator. So basically you can model this loop here as a control system again, because the PLL is after all a control system. So you can have the control transfer function and the error transfer function written down. You can see that it's a second order system. Second order systems have this type of behavior which is known, and then it's about designing. This is the natural frequency. This term over here, eta, which is the damping of how damping should be. Then you can have such laws immediately defined because this well-established concepts. And practically to implement, I found this really nice reference from Texas Instruments on how to implement PLLs in Discrete, and they basically explain how to design or design the continuous time PLL, then change it to Discrete, and then you have, so for example, this would be the Discrete time PI controller. And then based on the sampling time, you can calculate. So this part is B0, this part is B1. You can just compare these two. And so based on the continuous time controller gains that you designed, based on these principles and the sampling time that you use, you can immediately have your PLL design in this way. One thing that I, of course, assumed is just we are just looking at balance scenarios, because the unbalance is even a little bit more complicated than this, and there are a lot of references. You can just go and look into that. But this is just the basic idea of PLL, and even this is highly challenging to design. And basically, this is a virtual controlled oscillator. I'll just quickly say what that it does. It so it basically starts from 0 and goes to 2 pi and resets. So this is the angle. So it's the plot of angle with time. So it produces a sawtooth type of waveform. And one of the problems that I've noticed is because of this reset, especially when you do a discrete implementation, so you are just having some samples, runs like this. Of course, at some high frequency, let's say 10 or 20 kilohertz, and at some point you're going to have this jump. And because of this jump, this variable omega, the frequency, right, the omega, so this omega has some kind of, so let's say this is 2 pi 50, okay, omega is 2 pi 50, the typical one, and then you see these jumps happening, some ripples like this. And these spikes, you can get rid of them by using a notch filter, because I mean these spikes happen because of the reset happening, and the reset happens at the frequency of omega. So you need to have a notch filter which is adaptive with omega. So it's an adaptive notch filter which tries to, so notch filter has a behavior like this. So it tries to eliminate a particular frequency, and you want to get rid of this omega content in that estimated variable, so that you have a smooth response instead of those spikes. So this is just an example. There are many other formulations. For example, the grid voltage measurement could have harmonics. Then how to get rid of those? So it's an endless ocean of PLL designs, and this is the most simplest one, which is already super complicated. So now just to explain how PLLs are really affecting. So it all starts here, where you measure the grid voltage and try to convert it into DQ domain, as I explained here. And you see that the PLL's dynamics goes into the voltage signal of the Qs. And this VD and VQ, you will be using it in your control. And that's how it starts to propagate. So here this contains VD and VQ. So the main culprit is the VQ signal. And that will be used, for example, in grid voltage feed forward. It would be affecting the current variable, and these are the two terms how PLL dynamics propagate into your inverter. So this is the idea. And again, by using the generalized MIMO rule, you get the transfer function of the inverter with PLL, and you can see that these two terms show up, and this is how the inverter's impedance is modified. And why do we call it quite destabilizing is because of the negative resistance behavior. I'll just explain with a quick example. So I found this in a paper where they first found this in a phenomenon, I think 10 years ago. You can see that, so this is the impedance plots. As I said, it's a 2x2 system. You have 4 impedance, the matrix, right? And the Q axis is the one which gets affected. So you can see that the QQ axis has the phase at minus 180 degrees. That is a negative resistance behavior. That is exactly what you will find in a constant power load. We say constant power loads are destabilizing. This is why, because it has a negative 180 degree phase. That means it has a negative resistance. And that can, if there is a large disturbance, then you cannot say for sure that it's going to converge. It may diverge. That's why it is the PLL design is a big challenge. It's only because of this. So that was all about PLL, and now we'll look at an example of harmonic instability. This is just a example that I did 1 week ago, just for this to explain in an easy way. So just a MATLAB model of an inverter. So please don't mind if it looks shabby, but I can explain clearly. So this is the single phase inverter with 4 switches, and you have the LCL filter, which is the output filter of the converter, and this part is something that is unknown. It belongs to the grid impedance. This, I cannot see that straight. I just connected to the socket which I call as the grid, and then whatever impedance is there after that, I really don't know. So this is the grid impedance, and then here I have the control, the PWM generation for the inverter, and this is the complicated PLL part. But yeah, it's a very discrete domain design, as I explained. So the idea is to consider a grid impedance which is always there, and I considered 2 impedances for this. One, a really low value, which means it's behaving in a stiff way. It's an ideal voltage source. So if this is super small, then you have a stiff voltage source, and the inverter doesn't have a problem. But if this impedance is increased, then, as I explained already, the resonance shifts to the low frequency area where the control bandwidth is there, and the controller and the will start to react. So there'll be some problem. And this is a very dangerous impedance. Basically, if you have a RC here, then you have you're going to have resonance. So if you have just a second order impedance, it's already going to have some problems if the damping impedances are low. So when this breaker is closed, the impedance, I will show the impedance plot later, you will see that it actually intersects the impedance of the inverter, and the phase would be 180° apart, and that would cause oscillations. So this is the inverter's normal operation with the high grid impedance. So you can already see that it's not having a stable amplitude. It's already challenging this, push the system to the limits. And at 0.5 seconds until 0.8 seconds, I have the breaker closed to have this resonance into effect, and you can see the high frequency oscillations happening. This is harmonic instability. So I can explain better in the DQ domain. What I do is, although it's a single phase inverter, I do a split phase technique, just like how an induction motor starts. You need to have a split phase capacitor to start the induction motor. So same concept. I take the grid voltage, and I put a phase shift of 90 degrees to the grid voltage to create a imaginary beta component, alpha beta, and then it's just like mimicking a 3-phase system. So the controllers are in DQ, everything is like a 3-phase inverter once you do this small trick. So now in the DQ, so this is just a zoom plot of this region, just to show the high frequency ripple on the 50 Hertz signal. Okay, and then this is the DQ current. So in the DQ frame, it's DC, right? So it looks DC. So this is the current. The blue is the reactive current, the Q part, and this is the ID. So this is ID and IQ. Their references are maintained at 50 and -50. So indicating that I'm absorbing reactive power and injecting reactive power, reactive power, and you can see that already because of the existing grid impedance, it's quite challenged, and once the shunt path is included, you see the high frequency ripples. So just explaining in DQ domain how the harmonic instability looks like. And this is the plot that I was talking about, the impedance plot. The red one is the plot of the inverter, the closed loop impedance, all the modeling that I explained, the large equations of the matrix equations. Then you obtain this plot as a function of frequency, and you can see here this is the plot of the grid impedance, and because of the presence of the capacitor part, the shunt part, you can see the resonance here, right? And what is interesting is to look at the points where the intersections are happening. And for example, at this intersection at around 10 kilohertz or 10 kilo radians, right, you see that the magnitudes are 180 degree apart, or quasi 180, close to 180 degree, and that means this means that it's having harmonic instability. Another way to show is by the Nyquist plots. So you can see that it should never encircle. So this since the plots are quite covering a large values of numbers, I would show a zoom plot again. But the unit circle that I was talking about is somewhere here. So you can see that it's going really close. So if I show the zoom plot, it'll be better. This is the point where it should never encircle, but it's coming very close to the critical point, which means the stability margins are almost zero. That's why you have sustained oscillations when this happens. So you can see that this goes like this and back out like that. So this direction shows how the plot moves. So it goes in and then doesn't actually encircle, goes a little bit around it and comes back. So that's what we show here. It goes here, does something and goes out like that. So it's very close to instability. Now considering strong grid. So which means, if I just quickly go back, this impedance is extremely low, and then even if I close this combination, since you have a low impedance path, the impedance is not intersecting. So under the strong grid conditions, you see that this is the DQ current, by the way, so you can see that it's very stable, and these ripples are because of the natural current ripples that's there. When you design your filter, you always design inductors based on ripple currents. So that's the ripple that's there all the time. So it's not something that is related to harmonic instability. And then if you see the plot, now you can clearly see that it clearly misses this point. And if I show you the zoom version, if I have it, yes. So you can see that this angle is much larger. This angle is much larger. So we can compare. So here it's intersecting around -0.2 plus 0.2. If I go back to the strong weak grid condition, you can see it's very close to 0, right? So the angle is very small. The angle subtended from this line, like this. So here it's quite larger. So this angle is actually called as a phase margin. From 0, if I draw this line intersecting this point, this angle is the phase margin from the Nyquist plot. So larger the phase margin, more the stability margins. So lesser the margins, closer you are towards instability. So that was the example of harmonic instability. Any questions on that actually? Was this example convincing, or was it explaining the phenomenon? Okay. Passive response. That's a passive system, by the way. That's how you design. Okay, so now I just want to quickly explain what we're doing from the reserve perspective. So defining new role of inverters. So one, as I already explained, the dynamic voltage stability work. Inverters can actually behave as impedance measurement devices to the grid, not just something that injects power. It can, since it can measure the impedance, you can do so and relay it back to the grid operators for their monitoring. Inverters can participate in support by changing their set points, not just for power or real reactive power, but also by changing their impedances. So that was the idea. And for steady state voltage support, the colleagues from University College Dublin are doing this work. They're defining curves like voltage reactive power curves. So based on the grid voltage, they decide how much reactive power they should inject to support. And these curves are calculated by doing an optimization for minimizing power losses and unbalance. So multiple objective optimization. And then basically what we found from this work was that right now the grid code says you should always operate the inverter with 0.9 or 0.95 power factor, lagging, not leading. Some grid codes, maybe in Germany, they say you can operate your inverter at leading power factors, but very close to 1 though. But what we found was you can actually, in order to have an optimized operation, your inverter can do anything. Basically, so just to have a quick explanation. So if this is the real power, this is the reactive power. Let's say this is positive means injection, negative means that you absorb reactive power. So current grid codes say you just operate here, you just inject real power. But what we found that you can actually, for optimized grid operation, you can be anywhere. So an inverter can act like a capacitor. An inverter can behave like an inductor, absorbing reactive power. And so the grid codes need to be relaxed because the grid codes are very conservative, so they need to be relaxed. So this was the idea. So this is the key enabler. Because our project is about grid codes, targeting them. So the way you do that is by this. So in order for these techniques to come into picture, network codes are the key enablers. And our work has not only been just doing the technical work, but also trying to map the technical work to the network codes to understand what modifications and new network codes that we can bring about. So this was our approach in the project. And lastly, I just want to explain about a concept of a monitoring device concept that we have come up with. So let's say you have a distribution grid with many inverters. These are the cable impedances. This is the modeling of the inverter that I just explained. The current source and the inverter impedance, closed loop impedance. You could also have local loads connected at different buses. This is the model of Irish distribution network. And then let's say that if I'm interested in studying the stability at this node, then what we do is we propose an inverter or a device that can measure the impedance, small scale device that can be plugged into the grid at any point, has high plug and play capability, has communication capability to communicate the information back to the secondary substation automation unit, that's the SSAU there. So the idea is to inject perturbations here, have current sensors measure the current on either side of the injection node, get the voltage at the node, then you can get the impedances as seen from here, as marked here, Z6L and Z6R, which is equivalently represented by this figure. So now you can recall and you know how the stability will be done based on the two impedances. Then you can have all sorts of plots in order to have stability. This is just an analysis that we did wherein we played with the line lengths to just increase and decrease and see how coupling of inverters affects. So you can see that if the inverters are very close, so if the line scaling is small, it means the inverters are close, then you have smaller angles compared to when you increase the line lengths. So in this case, if the inverters are really far away and the impedances, the cables are acting as low pass filters and the grid is a strong grid as of now, you would have a passive system. This is what we can conclude from here. So this is one application that came out, and in order to have such a device, we are actually developing a low power prototype. So if you came for the visit, you would have seen this where I explained. We came up with a very modularized design. These are the IGBTs and gate drivers all in one, called as the new technology called as Intelligent Power Module, where the IGBTs and the gate drivers are within, so you need not do any design on your own. And then we tried to modularize to have the LCL filters of each phase as separate cards, which can be plugged in at right angles to this to this plane in this board. And we also made measurement boards which can be modularized. So small high bandwidth measurement boards, because we're going to measure high bandwidth signals of currents and voltage in order to calculate the impedance. So for example, this is how the finished product looks, and now we are in the testing and commissioning process of this. So this is the LCL filter board with the measurement cards plugged in. So as I showed here, this is one measurement card for DC link voltage measurement across the capacitor. Here you see that the filter board cards are plugged in at right angles, and all the connectors which connect to the grid and DC link are in this main board. So just a top view to just clearly show the filter board on which the measurement boards are plugged in. So that's our setup. And once this testing and commissioning process is complete, we would do a field trial in the Irish grid, and the setup would look something like this. So this box is what we have built within this dotted box with the inverter, the LCL filter. The inverter would be having all sorts of protection, PLL, and the control, and the impedance measurement tool as well. And so we have the possibility to either charge from an AC source or directly from a DC source to this DC link, or you can charge the DC link in this way. So we have 3 ways of charging, and the idea is to inject perturbations and get the impedance and analyze the quality of the extracted impedance. What we mean is how reliable this is, what are the uncertainties, something like this, an uncertainty analysis. So that's it from my side, and if you have any questions we can discuss.